In the case of thin film interference, what you're doing is you're looking at the interference once again between two waves, but both these waves are now waves that are reflected off an interface. So what a thin film does is to provide two surfaces at which, two interfaces at which the wave can reflect. So when you talk about thin film, it's something that's located between two different media. It could be a thin film in air. That means I have air here and something in between. It could be a thin film in water or some other fluid. It could be a thin film sandwiched between air and some other material like water or glass or something else. Okay, and in biology, it's very often, you're doing a thin film on, say, a glass plate. Or you have a film floating on a fluid. It could be water, it could be, some other solvent that you're using. What is doing the interfering is the waves that are reflecting off the first interface and the second interface. And therefore, what you're counting is really the difference in length between these two waves. Now, all the problems that you read will say near normal incidence. What does near normal incidence mean? Near normal incidence means that the wave is almost perpendicular to the interface. Why are we talking about near normal incidence? Because if it were perpendicular, right, it would go back exactly the same way it came. You say near normal because you don't want to worry about the angle in taking into account how long this path is. So really, if I were coming in at an angle, I should be taking cosines or sines of these angles to find that path length difference. But I'm ignoring that, and I'm saying this length is exactly longer by an amount equal to twice the thickness of the film, because it goes down and it comes up. So I'm making the approximation that the distance it travels in both cases is the thickness of the film. So then, again, remember I said what counts is the path length difference, and that's twice the thickness. So this is the first thing to realize, that the path length difference between ray 1 and ray 2 is twice the thickness of the film. The second thing to remember in this problem is that this path length difference is occurring inside the film. So if the film has a different index of refraction, then you have to worry about the fact that the wavelength of light in that film is the wavelength in vacuum divided by the index of light refraction. Okay, so 2 points to keep in mind. This is a summary of thin film interference. And so, if you look at constructive and destructive interference, you get two relationships. I'm going to describe this. And you can see in this second column over here, or this third column over here, I've switched these. Okay, so what is going on here? Remember, what I need to know is whether when these waves come out, whether they are in step or out of step. So a phase change of half a wavelength means they are exactly shifted by half a wavelength. They're exactly half a wavelength out of step. Okay, so when do they get out of step? It turns out when they reflect at an interface, the properties of the interface determine whether the waves are in step or out of step. They're sometimes called hard and soft boundary conditions. So imagine you have a rope that's tied at one end. You send a wave pulse. If you send a wave pulse, when it reflects, it inverts. And so imagine I have a wave pulse traveling this way. It hits the end of the tied rope. The tied rope cannot move up with the wave. So instead, the energy goes into flipping the wave, and it reflects. When it reflects, it does a half phase shift. If the string were not tied at that end, when the wave maximum reaches there, the string can move with the maximum. So when the wave reflects, it goes back the same way. It doesn't invert on reflection. So something similar happens with light waves at the boundary between two media. So when I'm going from a medium of lower index to a medium of higher index, it's like a hard boundary condition. It's like having a string tied at this end. When the wave reflects, there is a phase change. There's a half wavelength phase change. This wave is shifted by half a wavelength. Okay, so I'll say there's one phase change there. Now, if there is also a phase change for the second wave, then they are back in step, right? So then the condition for constructive interference is that the path length difference is an integer times the wavelength. So that happens if both change phase or if neither change phase. Because if only one changes phase, they are half a wavelength out of step. If the other also changes phase, then they are back in step. And so they will interfere constructively when their path lengths are different by an integer times the wavelength. Okay, so it's back to this constructive, and they'll interfere destructively if the path length difference is a half integer times the wavelength. However, if only one of them is changing phase, then they are half a wavelength out of step. So to interfere constructively, you have to add a half wavelength to the path length difference. What do I mean by a phase change? Say I have a boundary and I have a wave traveling to the boundary. When it travels away from the boundary, it flips. That's a half phase change. Okay, so this is a half lambda, lambda over 2 phase change. If it doesn't flip, if it goes back the same way as it came in, so if it did this, so let me draw the full wave. So it's coming in this way. When it reflects, if it goes back that way, then there is no phase change. Okay? It goes back the same way that it came. If it's coming this way and it goes back like that, then there's lambda over 2 phase change. That tells you that when I do have one wave changing phase but the other is not, because they're out of step, imagine one doesn't have a phase change and one does have a phase change, then you see that they're going to cancel each other out if they're shifted by an integer number of wavelengths. So you have to shift them by a half wavelength in addition. So the condition for constructive interference in that case, that the path length difference be equal to a half integer times the wavelength. So if I'm going from air to gasoline to water, where I have air is lower than gasoline and gasoline is higher than water, the index of refraction, how many phase changes will I have in this particular picture over here? So there'll be a half wavelength phase change. That means that's the condition for only one wave ray 1 is changing phase. Ray 2 is not going to change phase when it reflects here. So then the condition for constructive and destructive will correspond to the second column over here. But suppose I had, so this would also be the case if this were a thin film of oil in air, because I'd go from air to something of higher index back to air, which is of lower index. So once again, if I just have a thin film in air, this second column is the formula I would be using. However, if I have something on glass, let's say oil on glass, and oil has index 1.4 and the glass has index 1.5, then I will get a phase change here and another phase change here, and therefore I'll have two phase changes, and this is the formula I should be using. For both cases, you can have both constructive and destructive interference. The question is, which wavelengths will have constructive interference and which wavelengths will have destructive interference? So in the problem on this week's discussion sheet, for example, I give you one situation and I ask you to find both constructive and destructive. I ask you to find the wavelengths at which you have both constructive and destructive wavelengths, so interference. So the question is, which colors are you going to see and which colors are you not going to see? The colors you see are constructively interfering. The colors you do not see are destructively interfering. Does that make sense? So both are happening. Some are getting cancelled out, the destructive interference, and some are getting reflected, constructive interference. So when something appears blue, it's because blue is interfering constructively. So a lot of phenomena you see in nature are because of thin film interference. Often you see color because materials absorb wavelengths and reflect others that they don't absorb. So you don't see the wavelength that's absorbed, okay? But if you look at bird feathers or butterfly colors, the reason bird feathers, the brightly colored bird feathers you see, or the butterfly wings that are brightly colored, that is a thin film interference phenomenon. Another phenomenon that you see because of thin film interference is, has anyone heard of the B-2 bomber? The US Air Force has this plane. Okay, so what is special about the B-2 bomber is that it is invisible to radar. Okay? But as Dave Barry said many years ago, it is easily picked up on ordinary television. So it's not invisible to optical wavelengths, but it is. So it's hard to spot it. And why is it invisible to radar? It's because they coat the bomber with a thin film of a material that has destructive interference in the radio wave range. So if radio waves, which is what radar is, are bouncing off the plane, they interfere destructively, and so they can't be picked up by the radar detector. So it is something that has a lot of application, and people use it in various ways. So of course, you also see it when you see pretty colors on a puddle of something or in a soap film. Right, so this particular example, remember, is the case where I have one phase change. So when I have one phase change, they're already half a wavelength out of step. So if the path length difference is an integer number of wavelengths, then they are half a wavelength out of step, and they will interfere destructively. So this is the condition for destructive interference. Now, how do I figure out? So in the problems I ask you, very often I'm trying to figure out which are the wavelengths in the optical region that interfere constructively or destructively. So for that, you should remember that the optical spectrum, the visible spectrum, is approximately 400 to 750 nanometers. So when I'm asking you for colors that are absent or present, that's the range in which you're thinking about the wavelengths. So what you would do in these formulas, maybe I should go back to these formulas, is to find the right M which would give you wavelengths in that range. Okay, so try doing the problems on the discussion sheet this week. If you're able to do the last two problems, then you have understood what's going on here.